Okay, let's see if I can finish this example before class, because I'm calling it close. So we have water that's sloshing back and forth in a tank here in this condition right here. And we want to do the dimensionless groups to find the relationship of the natural frequency of the sloshing to the various parameters that it might be dependent on. And they say here, they tell us that, well, it makes sense that gravity is going to come into play, right? So it'll be different if you were on the moon than on the surface of the earth. The height of the liquid and also the length of the tank are important variables. And they tell us that the gravity and length are the repeating variables right here. So this is a simple example. We should probably go and look at a more complicated one before we go too much further. So the first thing first, I did most of these steps here to try to make it a little quicker in class. But step one is I wrote out the variables, and then I counted them, and there's 1, 2, 3, 4. Therefore, k is equal to 4, right? The thing that I've defined as k. Then I write out in step two, I take a look and see what are the dimensions, what are the fundamental dimensions right here. Well, this is radians per second, so the radians don't have a dimension. So that's time. And then gravity is, of course, length per time squared. H, that's just length, and then length is obviously length. So there's only two parameters right here. There's only L and T, right? So only L and T. Therefore, R is equal to 2. And so in step 3, we have the simple equation that K minus R is going to be equal to 4 minus 2. Therefore, this is equal to 2. Therefore, we can expect that there would be 2 pi terms. Therefore, 2 pi terms. And step 4, they've already given it to us. So this was given. Is G and L. I don't know if I want to go. I guess I'll use their L. Why not? I'll use their L because it'll make it confusing here. Okay, so I like to put it up in. I've also included, if you wanted to know, how do you choose if you weren't given G and L? How would you know? Well, first off, you don't want to be too redundant. We'll see that coming up soon, right? So these are things that we might kind of consider when we look at other examples. So you don't be too redundant. Like if the other variables besides this is the primary one, and then we want to look at for the other two. Like we wouldn't pick H and L because they both have the same dimension. And because we want to repeat every basic dimension at least once within the non-repeating variables. And then we want to take the simplest combination of the basic dimensions is going to be the best. These rules really for more complex problems if you wanted to do this on your own. So step 5 is to really assemble the first pi term. And what we do is say pi 1 is going to be equal. Now we use the primary variable for step 5. The primary variable is omega. And then we put the repeating groups inside here, and they're raised to the exponents, A, B, and C. All right, and for us, that's going to be G and L, and we don't have a third one, so we don't need this, right? And then down below this, we're going to say, well, we write down what's up here inside there. So we say this is T minus 1. G is going to be LT minus 2. Oh, I gotta try to fit that in there. Come on. T minus 2. So you can see it. And then up in here under L is just going to be L. Right? And then that one doesn't count. And then down below this, under M, L, and T, we have these rows. We're going to isolate the exponents in here, right? So first, there's no mass. So there's 0, 0, 0. Obviously, this one is 0 because we've already crossed it out. And then we said it's equal to what it has up here, 0, right? So that was just for the mass. We see there's no mass involved, so 0 everywhere. The L right here, there's no L inside here, so he's 0. There is one L in here, so that's going to be A, right? So this is going to be L raised to the A, so it's just right there. And then we also see that L right here is raised to the B, right? Because there is an L in here. So there's a B right here. And then there's 0, obviously, and then there's 0. Our conclusion from that is A plus B equals 0. A plus B equals 0. This is going across right here. This is the equation for the exponents when it comes to L. And therefore, A is equal to negative B. Do the same thing for time. All right, so here's where we're going to be able to solve this, right? So we don't know what these are yet, but here, because this one shows up right here, this is actually a -1, right? There's no letter up here to the exponent, so this is -1, and then we see that this is -2a, right? Because we have t raised to the -2 raised to the a, that ends up being -2a. And there's no time here, and then this one, of course, is there, and that has to be equal to 0. Therefore, we say -1 minus 2a equals 0. And therefore, a must be equal to -1/2. And then because we had this rule up above, we know that b is equal to 1/2. What is our conclusion from this? Well, we can plug it right back into this guy up above, and we could say that pi 1, I wish I had put some more space in here, by the way. Pi 1 is going to be, well, it was always going to be omega, but it's going to be g raised to the a, the -1/2, and then L raised to the 1/2. And so another way to write this thing out, maybe, I guess I can make him fit him in here. Pi 1 is going to be omega square root of L over G. So we've just made our first pi term. Now, we only have 2 pi terms, so in step 6, we only have to do this once. We do the same thing for the other non-repeating variable. And remember, the repeating variables were G and L, so the only variable left is H. So we do that here for H, right? Put him in there, and then put G and L, and then we don't having anything for here. And this one's going to be pretty obvious, right? Because this one's L right here, and then this is going to be LT minus 2, and then this is just going to be L, right? And then there's nothing there for that one. And by the way, you could just guess this pi term. It's just going to be the ratio of H to L. That's what we're going to end up finding, just so you know. And that happens a lot because when you have multiple lengths within something, the pi term is almost always going to be a ratio of the dimensions because they cancel each other out. They're obvious, right? They're dimensionless. So, but working through this system, we go for M again. We kind of knew that was always going to be 0. That one's obviously 0, so we want this to equal 0, everybody in this column. And then for here, we're just going to say, well, that's just going to be 1. And then for the L, we could say that this is going to be equal to A. And then right here, this is going to be equal to B, and we're a little concerned. We're like, well, what's going to happen there? I don't know. Well, we'll see soon. That one's 0 because there's nothing in the C component at all. And then to go over here for T, we'll see that this one is 0 right here. It's going to be -2A, and then 0, right? There's no time in there, and then this one is 0, equal to 0. So for this first one right here, we see this a little concerning. 1 plus A plus B equals 0. And we're like, ooh boy, that's not sure what to do with that just yet. So put a pin in that first. Come down to here, and you say that -2A is equal to 0. Therefore, A is equal to 0, and therefore we could have canceled that out. So what we find from right here is that B is equal to -1. Therefore, our pi 2 term, we plug these in here, H times, this is to the 0 right here, so that just turns to 1, and this is L raised to the -1. So we have as pi 2 is equal to h over L. So this is an important step. If everything worked correctly right here, we're going to find this. Let's take our pi 1 term and just look through it right here. So I find that it's going to be best if you write it as a straight line, but plug these guys up here back into here to double check that you got it right. So we got t negative 1 right there. We're going to have L to the 1/2, right? So he's going to be L 1/2. And then this guy, he's on the denominator, so he's going to be negative. So and we're square rooting him, right? So he's going to be the L to the negative 1/2. And then the t here, right? This was a t that was negative, but he was -2, right? But he was on the denominator, so he comes back up. So if you need to do this in multiple steps, you can just trust me right here that this is going to be a t, a +1, right? Because he was a -2, but you square root him, so he got the bottom. And he was a negative, but then he came back up on the top, right? So he was in the denominator as -2. He comes back up at the top as a +2, and then you square root him, so he's going to be right there. And then you check these out, and you'll see they'll cancel, and they'll cancel, and that one's fine. And this one, you could just, we could just tell. We know that that's going to be L and L -1, so they'll cancel out. So the last step here is to just make a statement of what we have found. That, well, I guess maybe I'll write this. Pi is equal to pi 2 right here. That's what here, but that's not what we want to write. We want to write this guy over here. Then we're say that what we've learned is that omega square root of L over G is related to H over L. And by the way, we could have picked L instead of H as our primary, and this would just have been the reciprocal of it, and it wouldn't matter, right? Just a note. But here is what the solution is, and here's what we're out to get. That's our mission right there. And then what we could do is we could run an experiment and verify that the natural frequency for a particular setup right here, we could have we could graph these out, right? We could find some type of graph. I don't have a place for a graph, but we could have a graph out H versus L, and we could have natural frequency square root of L over G, and it might form like it could be a straight line, it could be a curve. We don't know. It might actually trend the other way. I don't really quite recall. But that ratio of the depth to the length is going to be something, and we can go, because we'll know the length in that case for our situation and gravity, and we could predict what the natural frequency of this scenario is going to be from a series of experiments. Instead, we might actually be able to find this particular thing using first principles, but they should be in agreement with each other. Sometimes you might have to create a correction coefficient if something like that doesn't happen. So, and we'll see that with various other problems. But this is your first Buckingham pi example, and we'll do some more so that you'll feel more comfortable with it. But the best way to really learn this is to do some problems yourself, and hopefully you'll be doing that for homework. So the end.